we develop a human character capable of searching for a randomly located target object in a 3D scene, using its locomotion capability and egocentric visual inputs. Living rooms, kitchens, bedrooms, supermarkets are full of objects which we frequently need. And oftentimes we don't know in advance where some of those objects are. And object searching is a rudimentary task that people perform on a daily basis multiple times without too much thought. However, when it comes to computer animation, the approaches we can take for animating characters doing searching are not particularly clear. One of the approaches could be prescribing search and control logic, but it's hard because of the large configuration space. And also it might not look natural or human-like. And with existing full-body motion imitation models, it's not really clear how to use or adapt them for the searching behavior. In computer graphics, a conventional character search animation would use full knowledge of the 3D environment and achieve optimal path movement. In robotics, the robot would be able to travel to the object directly once the object is found. However, it would use random noise to search for an object and do exploration. In either of the cases, the motion would look natural. With computer animation, it will be supernatural because agent knows in advance where the object is. In this work, we take exploratory steps towards seeking for a learning-based approach from which human-like behavior could arise. We ask a question whether we can develop algorithm that enables searching behavior in animated characters or robots. Unlike traditional approaches that use full knowledge of the environment and often know the object location in advance, we deprive the agent of object location information and only allow agent to perceive the world via camera. Our method consists of two components. The first component is the learned searching policy. We first train a simplified version of an animated character with egocentric visual inputs to search for an object. We use an abstract agent which is represented by a cylindrical shape with a camera attached on top. It can move around the environment and control its head similarly to the human character. Once the abstract agent is trained, we then demonstrate how we can reuse or transfer abstract agent's behavior to animated characters or a robot using motion replanning and synthesis algorithm. We will start by first looking into learning the searching behavior. Some of the traditional related work in navigation that assumes the knowledge of the object location, like SLAM combined with RRT star for mapping and planning, cannot be applied here, since we deprive the agent of the goal information. However, learning-based navigation approaches like DDPPO, with some modifications, can provide us a lot of building blocks for learning how to search. As an environment for evaluation and training, we will use photorealistic scenes from iGibson Simulator, which provides us a dataset of a variety of indoor environment scans. We augment the houses with additional furniture that is relevant to our task, such as cabinets, which we can use for object placement, in addition to placement of objects on existing surfaces like countertops or the floor. The objects during training and testing can be placed on any of the surfaces within the environment. The agent is tasked to find one of the objects that is predefined in the beginning of the rollout. Next, let us look into the states and observation spaces of the agent. For a given time step, from the environment state we can extract a history of last 5 depth channel observations, each of size 84 by 84 pixels, object segmentation mask such that the agent knows what object it is looking for, and proprioceptive information of its head joints, such as pitch and yaw angles. To reduce the dimensionality of the state space and force the agent to learn a policy agnostic to the object shapes, we pre-process the mask channel. Specifically, we downsample the 84 by 84 array to size of 5 by 5, which simply means that the agent needs to pay attention to a specific region as opposed to a particular set of pixels. After the processing, the mask looks as following. 5 by 5 binary array with 1s over the object region and 0s elsewhere. Next, we will look into the rewards used for incentivizing the searching behavior. The rewards are inspired by the related work from the area of learned navigation. There are 4 different terms that are used for calculating the reward. First one is the success reward, which is given if the rollout is successful and not given elsewhere. We will look into what exactly success means in the next section. Next term is delta distance, which is positive when the agent takes steps towards the object, and negative when the agent takes steps away. Third term, called life penalty, encourages the agent to complete the tasks more efficiently. And lastly, we want to avoid any collisions while we are performing the tasks. Hence, we add a term for penalizing any contacts between the agent and the environment. We will now define the termination condition for the training. For the task to be successful, the agent needs to meet three conditions. It needs to find the object and keep the object in the field of view. It needs to be within certain distance from the object, 0.5 meters in our case. And it needs to do that within a certain time frame, like 100 time steps. If first two conditions are not met before the time ran out, the task is considered unsuccessful. Next, we will look into the whole pipeline used for optimizing the agent using reinforcement learning. At each time step from the scene state, we extract the observation information as described earlier, which is depth and semantic segmentation. We then downsample our mask information and extract the pixel coordinates from the object location. We concatenate all of those features with proprioceptive observations of the head joints. And those features are fed into a fully connected neural network that represent a policy. We use convolutional neural network to extract feature vector from the depth observation, which are also fed into a policy. With all of those components combined, we can now use a reinforcement learning method such as soft actor critic for optimizing the policy behavior. In order to be more sample efficient, we can also use recent advancements in unsupervised learning domain. One such approach we use is called curl. Curl uses contrastive learning and augments soft actor critic algorithm for learning effective features from high-dimensional pixel inputs. We will briefly go over an equation of contrastive loss that is used in curl. There are two CNNs that will be used to generate feature vectors that will be used for loss calculation. Those CNNs are called key encoder and query encoder. To calculate the contrastive loss, we will start with an image. This image will be cropped randomly and processed by a query encoder. The features produced will be stored in vector named Q. Another random crop from the same image will be processed by a key encoder, and the features will be denoted by K+. These features will represent a positive matching pair of the query features. We will sample a number of additional images different from query image. Those will be our negative samples. Random crops from those images will be processed by a key encoder, and they will be labeled as negative samples. To define our loss, we will use a similarity measure, which is a dot product of two feature vectors. The name of this specific loss is INFO-NCE, standing for noise contrastive estimation, which can be thought of as the log loss of a k-way softmax classifier, where the similarity score between the query and the positive sample is normalized by the sum of the scores of itself with the similarity scores between the query and the negative samples. The intuition for this loss is to encourage the encoded latent features of queries and keys from the same time instance to be close to each other, while being far away from the latent features from different time instances. There are multiple ways of measuring the similarity between the query and the key pairs. In our work, we use bilinear product for measure calculation. It introduces additional learned parameters for similarity measure calculation. For additional details about the contrastive loss, please refer to the original curl paper. While during training we use two CNN encoders, during testing we only need one for feature extraction. Okay, now we'll go back to the whole pipeline. During the optimization, the contrastive loss is jointly optimized with soft actor critic. On this picture, you can see how the policy is trained by the RL loss, key encoder is trained by contrastive loss, and the query encoder is trained using both. Once trained, the policy can be directly deployed on the fetch robot in the simulation. Let's look at the example. In this example, the robot is searching for glasses which are placed behind the kitchen counter. Here we are looking at the same rollout again. On the top right, you can see the depth information that the robot observes. And on the bottom right, you can see the semantic images. You'll see how it sees the glasses right before it finds them. Now that we have a searching policy that works with an abstract agent, we can start thinking about how we could deploy this policy with more complex creatures. Policy that works on the abstract agent cannot be directly deployed on the full body motion character because of the differences in the action space. Even if we use trajectory that is generated by an abstract agent, while motion generation policy will be following that trajectory, the head motion will not be relevant to the task. The head motion will be guided by task priors, for example walking, and not searching, which will be suboptimal for the search task. We hypothesize that the head plays a critical role in learning the searching behavior in the animated characters. We verify our hypothesis with a pilot study. We train two agents, one with enabled and one with disabled head control. At the end of the training, we can notice that the agent with enabled head outperforms the other agent by about 20% margin. In this section, we will walk through the algorithm that we propose called motion synthesis and replanning. We will use an abstract agent that will be placed in the environment with some obstacles and the target object. We will use this 2D toy problem to help explain the algorithm. The blue circle is going to represent an agent, and the arrows will help you understand the orientation. The agent will traverse the trajectory. In addition to transitions of its body, during the rollout, the agent also controlled the camera. We can see the cameras using this green box and yellow field of view representation. Now we have this trajectory that is traversed by an abstract agent. We can give this trajectory to a motion generator. This trajectory is going to be a future trajectory that the motion generation algorithm expected to follow. Our humanoid character will start in the same exact position as an abstract agent. Then it will attempt to follow the trajectory that abstract agent has followed. If we visualize fields of views observed by a humanoid character during the trajectory following, we can see that the motion generated by the motion generation policy simply follows the walking dynamics. And we can see that there is a huge difference between the abstract agent's head behavior and the head behavior of the motion generator. Head motion follows the behavior as if human was walking along the path and not as if it was searching, which is suboptimal for the search. Head orientations from the abstract character in green and yellow cannot be directly reused for the motion generated trajectory heads in gray and green, mostly to the fact that the trajectory might have deviated from the original proposed trajectory, and also due to the fact that there is a difference in frequency between the abstract agent's trajectory and the motion generation trajectory. What we propose to do is we propose to set an abstract agent in each of the motion generated traverse locations and use the generated actions to override the head motion. We will get rid of all the head configurations from the traverse trajectory. We will bring back our agent and its abstract policy into play. We will set our agent into the exact position as the character's head orientation and root configuration. From that character's position, abstract agent will observe exactly the same scene as the original character would observe. We will render the environment and add head configuration joins such that they match abstract agent configuration space. We will query our policy for a new action. We will get delta root for transition and delta head for the head control. We will use the delta head action and combine it with the current head configuration of the animated character. The result of the operation will simply override the next configuration of the head. We will simplify our motion generation into this simple box represented in green. Now that we have next configuration for the root and head, we can continue synthesize the motion. We will place our abstract agent again in the next configuration, and we will query the motion synthesis function again to override the next head configuration. We will continue doing that for all the states until we reach the end of the trajectory. By the time we reach the end of the motion generation trajectory, we will have a head motion that would be following the searching behavior as opposed to the walking behavior. With this slide, we can see the difference between the normal walking motion, which is mostly looking forward because it tries to follow the forward trajectory path, and the search policy behavior, which tries to look around while navigating the trajectory. The algorithm can be applied iteratively until the object is found or the time has run out. The abstract agent will be set to the latest motion generation configuration and continue planning from then onward. Once the trajectory is ready, the trajectory will be fed into the motion generation planner. The planner will propose a path, and we will use motion synthesis again to regenerate the head orientations. Using motion replanning and synthesis algorithm, we can transfer the searching behavior from abstract agent to more complex human motion and other characters. Since the characters can be of a different height, we apply domain randomization during training of the searching policy. Please refer to the paper for additional details on training and domain randomization. We'll now look at the results of combining abstract searching policy with motion generation models such as NSM or PFNN. In this example, the character will be tasked to search for its glasses. The glasses are behind the kitchen counter. This is a replay of the same trajectory. On the right, you can see the images that the character observes. In this example, we will see how the character finds the object, then loses it, and then recovers to go back and find it again. We will rewatch the same trajectory again. Pay attention to how on the right bottom, the character can see the mask of the object. It gets close, and then it gets out of the view. It turns around, looks for the object in the whole environment, and then comes back because it sees it again. As you might notice, the character didn't really need to go around because it already saw the object, but because our agent is memoryless, that's why the agent forgets that the marker was there. And lastly, we can deploy our agent in a different room. In this case, it's a bedroom with a connected bathroom, and the object is hidden in the bathroom on the floor. Now we will talk a little bit about the evaluation. The performance of the abstract agent, as we saw earlier on the left. We also evaluate different heights of the agents and report the performance for each height configuration in the table on the right. From the table on the right, we can say that high camera locations give agent better view at the scene. It's harder for shorter characters to see the objects placed on the surface above their height. And lastly, from the table on the right, we should notice how short agents have hard time finding the objects that are outside cabinets. Most of the time because it's simply not plausible for them to find those objects because they're too high. While there is no good metric for measuring how natural or optimal the searching behavior is, we can use a performance metric used for object navigation tasks to measure how efficient we were in finding that object with respect to trajectory length. The metric is called SPL, standing for success weighted by shortest path length. Number n in the metric represents the number of trajectories that were generated by a policy. S represents the success indicator, whether the policy rollout was successful or not. L representing the shortest path length, as if we were planning using RRT star or A star for an optimal trajectory. And L is weighted by max of L or P, where P is the agent path length. Using this metric, we can show the importance of the long-term trajectory planning, and that simple noise-based exploration is not sufficient for finding the object in the desired environment. You can see how our algorithm on the right of the blue dashed line outperforms the algorithms on the left, which are considered baselines. Baselines consist of a single-step planning and noisy search behavior. And on the right, we can see that the larger number of abstract trajectories generated by an abstract agent is required for smaller values of n, which is a trade-off for higher SPL. We invite you to check our paper for additional details about the baselines and algorithm evaluation. We hope that our research inspires the future work in the direction of learning behaviors for the computer animation and robotics. Some direct extensions might involve more complex scenes and searching scenarios, agent accompanied by a memory, or the scenarios where the task is more complex and requires character interaction, for example, opening the drawers for searching for an object. This is the last slide, and we would like to thank you for your attention. Please use the link on the screen to find more details about this work. Thank you.